start.
Okay, so Norman, maybe you can
Yes.
start your presentation.
Yes. Okay, could you see my screen?
Yes, we can see.
Okay, so let's start. Okay, so my pleasure today to talk about the largest innovation cycle ever at MSc. So it's a journey into the innovation cycle 3, which is IC3, a short name. So I will, whoops, you want me to start the camera, I think, yeah? So you can see. Okay, start again. Okay. So this was managed by folks at CCMEP, which is Canadian Center for Meteorological and Environmental Prediction in Dorval, so MSC, Meteorological Service of Canada in Environment Canada, Climate Change Canada. Okay, so today I will talk about a bit about us, okay, just to let you know who we are and the way we do technological transfer, and then description of the IC3 itself and some epilogue after that. So CCMEP is a critical part of MSc in a sense. We are operating numerical weather and environmental prediction models. So we forecast, in fact, do numerical forecasts at the atmosphere, ocean, land, and rivers condition from the very short term nowcasting to seasonal forecasts up to a year in advance. So we provide the official numerical guidance for Canada. That's what we do. So we're based in what we at CMC in Dorval. So an example of a current suite of our numerical system. Don't be afraid by that. So I will explain quickly what it is. So it's a link here. It's really the number of systems that we are running now. So it's not just a regional model and a global model, numerical weather prediction model. Now it's much more than that, okay? So for example, if we look at the different system there, so what these systems are predicting weather, okay? So we have global ensemble, global deterministic, and all sorts of other systems that predict weather, which was used to be our main mandate. So now also we have air quality systems, okay? So forecasting the quality of the air over Canada and now also over the globe with the ozone, okay? We have also ocean systems now, and it's more and more included in the main system in the sense that it's coupled with the atmosphere. So a lot of oceans as well systems. We have as well waves prediction system, storm surge prediction system, and hydrology now prediction system. So you can see it's much more than just weather nowadays at CMC. How we do the tech transfer? Well, we work closely with the atmospheric science and technology branch, okay? And we're doing R&D work for many years. Then we identify the innovations that we want to implement to operations, okay? So we test these systems together, and there's a lot of presentation, scientific presentation. And there is, what is very important, there is a committee, which is called CMOS, which is, it's a steering committee that decide what proposition will be implemented in parallel run, okay? So we test that, and then we come back with scientific, again, evaluation, and come back to CMOS for operational implementation. So then once it's operational, that it's providing the official forecasts for Canada, basic numerical weather forecasts for Canada. Okay. That's the idea. So the strategy of an innovation cycle in that context, okay, we are trying to modify these systems all at once, okay, and only once per 1 or 2 years, okay. So as you can see, we have seen by my schematic, we have now more than 30 operational systems with different flavor, as I described. So it's a big challenge, and we have a large number of dependencies and coupling between these systems. So we need to do numerous tests to test the impact on the dependent system for every modification we made. Okay, so because they are linked together, that's why we want to diminish the number of tests, and it's more efficient to do the changes at the same time. Okay, but as you can imagine, doing that thing at the same time is a big task. So, for example, the GDPS, the Global Deterministic Prediction System, which is responsible for the official forecast in Canada for day 3 to 5. Okay, you can see that it has 18 children and grandchildren. So if you do a modification to the GDPS, then you have to test all these suites of systems because you don't know what will be the impact of that change to the rest. Okay, so you can see it's something. So our innovation cycle, if we give some detail of this process, the tech transfer process. So there's a part which is related to research and development, so planning, developing the system, integrating and testing, and delivering the system to operational department, the division. So we install that, we run parallel run, because of course we have to still provide the official forecasts with the current system. By the time we test the new one, we monitor and verify. And this takes about a year to do, okay? So with the number of production systems, as you have seen, the complexity, it's difficult to imagine that it could be shorter than that with the current framework we have, okay? So IC3 itself, so it's more than 170 innovations in 30 plus systems. We got this committee, steering committee, CPOP meeting. We have 15 formal meetings for that. So between March and November 2021, 51 scientific presentation, a lot of IT manipulation, of course, a lot of GitLab tickets, and more than 170 internal meetings. So it's a huge project, okay? Was a huge project. So innovations themselves, so we got a lot of innovation with major impact. There are many in the global and regional systems, both deterministic and ensemble, and in an environmental system. I think Sasha will describe some maybe in the next presentation. And for more detail on that, you can go to the MSc Open Data portal, and you have information on that. So today I will focus mainly on the premiere. Okay, so world premiere and Canadian premiere that we do during that changes, that update of our system. So first one, which is very I'm very happy to announce that now we have ensemble systems that are simulate the uncertainty in the GEM model, in our Canadian model, with perturbation of physical parameter. Okay, that's something I dream of for many years. So now it's first system in the world in operation to use only to use that approach. Okay, so instead of perturbing the total tendencies produced, it's now closer to a real stochastic physics. With an ensemble system, you want to simulate the uncertainty, and that's the way. That's a more comprehensive way to do it. Okay, so that's one part. So that led to a significant upgrade, especially close to the surface, near surface atmospheric variable. So it was a big improvement, especially for the JEPs. Also, a couple of things related to rivers. Okay, so now there is a dam management process, let's say, a method that is using the ZTR method, which is a way to simulate the way the dam are managed to forecast the correct river flow. Okay, that's one thing. So that's the first as well in the world. And there is also a couple of modification to the water cycle prediction system, which is the first operational system became the first operational to include ice loading on the river flow forecasting, and as well the introduction of wave parameterization for the computation of wind stress and turbulence. Okay, so what is the WCPS, which is a very neat system in a sense that it's hydrology, ocean and atmosphere system. So it's driven by the atmosphere, and we run ocean model. Okay, and as well the atmospheric fields are provided to hydrological model WATRU, okay, for these domains, so Great Lakes and as well Gulf of St. Lawrence. So this system is a very it's let's say one step closer to Earth system model, let's say. Also, last world premiere we had is now in the GDPS, the global deterministic system that they use to do official forecasts in Canada, day 3 and 5. So it's use now background error statistic purely from ensemble. So we do the data assimilation based on statistic purely from ensemble system instead of prepare fixed statistics. So it's something that very interesting, because in a sense it's following let's say the weather regime. So these stats are adapting to the weather. Also, and in this system, we now assimilate a chemical component, which is the ozone, okay, and it's used now to do the we're providing UV index forecast. So this has feedback on the weather field. So that's the first that chemical has an impact itself. So it's a 3D now ozone global analysis. And also, yes?
1 minute.
1 minute. I think I have double slot, so I think it's up to.
Yeah, Ron, I think this is an invited talk, so it's 30 minutes.
It's okay.
Okay.
Yeah, go ahead.
Okay.
Sorry.
Thank you. Yeah, so the assimilation now, first for our center, we assimilate satellite data for all sky, in the sense that not just for clear sky, but with also in cloudy air. Okay, usually it's a big challenge to use these satellite radiances in cloudy air. So now it was the first step toward that, and we hope that it will improve a lot in the coming years, okay, with adding more and more of that data. So it's just an example. So since that time, this system, global model, is now well, second in North America, behind the European model. So it's performing quite well since that time, since these upgrade. Okay, used to be as well in the top 3, but now it was second. Okay, so other important premiere is adding the atmospheric data estimation in the HRDPS, so 2.5 kilometer resolution. So used to be just started from an analysis at 10 kilometer. Now it's 2.5, and also this is the first that we use radar data to influence the meteorological field. Okay, so in HRDPS, it's really now taking into account the radar data. As well, there's another modification to the Canadian precipitation analysis, CAPA. Okay, now we're taking into account the satellite data. So for the HRDPS, you can see a score here is the root mean square error. Okay. standard deviation of the error for the geopotential height in the verticals. You can see from 1000 millibar to 10 millibar, and the red line means it's the new system. The blue line was a previous system, and you can see it's better all the way from the ground up to 200 millibar. As well, we add a new parameterization of orography, and you can see the impact in the Rockies, where the temperature now it's colder, and the incoming warm air from the ocean is penetrating less deep in the valleys, which is more give more realistic precipitation type, like snow forecasts. So this is the grid of the HRDPS covering most of Canada. So how we communicate this big project? We have live presentation, we question and answer with our clients. We have a lot of web pages on the MSC Open Data web portal to announce the implementation, and a lot of documentation as well on these 30 systems, more than 100 documents, and it's available there. One thing that is new with this implementation is now we have a fact sheet for systems, so that it's describing in a one-pager, it's a system summary and specification and the changes that were made, and as well some main relevant results. Again, you can find these on the MSC Open Data portal. So that was very appreciated by our clients. So in summary, this is the biggest operational implementation by MSC by us. Times are changing fast. In 2015, not a long time ago, we had a big mega implementation. We called big mega at the time. It was only an update to 5 systems. So you could see that it has grown a lot. So IC3 is probably the largest implementation ever for NWP center in the world at the same time. Okay, so because now we have different domain, not just weather. Okay, so we're very proud of that accomplishment, but it was a stressful project, and now we have reached the limit of what our teams can deliver and maintain in terms of complexity and the number of systems. So we have now to simplify that. So the lesson learned from this huge project, so increasing number of and complexity of systems and their interdependencies limit what we can accomplish with current resources. So this is quite similar to other centers. So we have also an update schedule with the supercomputer on a 30-month upgrade frequency. And this is a major constraint on the way we do innovation cycle. And this is a big challenge, well, big constraint, yeah. We must work to simplify our systems and optimize our technology transfer. As well, the scientific coordination of the project was excellent, but the critical need, we need now a full R&D project manager. Now it's on occasion that we have that, but we need a full-time one. Communication with our internal customer was quite good. However, we have to improve that for external customer, and we got some feedback on that. So in summary, we were successful in implementing a very large scale improvement and innovation project between February 2020 to December 2021. So IC3 enabled the implementation of numerous modifications to operational system, which result in improvement in various numerical guides and the quality of the forecast and service offered by MSC. You have noticed that 2020 was in the middle of the COVID, so the original schedule was largely respected despite the fact that people work from home. So everybody was working from their home, and still we managed to deliver that. There were other challenges as well that comes with the huge project like that. So as an epilogue, I know that there is a session on digital Earth system. So I think the vision of building that system bring its share of additional challenges. First one, the connection and validation of a large number of very different components working together and in an interconnect way is a big task. Also, we need to share fundamental values, a common culture and common working methods between multitude of groups of scientists from various backgrounds, okay? As well, the growing complexity and the coupling between bring additional needs in terms of expertise in data architecture, standardization, integration and planning, and code management. We need to move to a sophisticated methodology for managing complex systems. In a sense, we have to move from a more laboratory mode to more an industry mode, okay, in the sense, because now it's not just 1 or 2 models that we're running, it's 30 more. So that's about what I have this morning. Well,
Thanks, Termon. I was just talking to Francis Weirs. He was supposed to be convening this session, but he sends his regrets. He had a issue in another session. So
okay.
we have lots of time for questions. You can ask them directly. Just turn your camera and mic on and ask them directly, or ask them in the chat.
Don't be shy.
My name is Yu Ping. Yeah, I didn't get the first part of you because my computer is a bit problem. I just this IC is it now or still it's all on operational sleep.
Sorry, Ruping, I cannot hear very well. I think maybe you can repeat that because it's
or type your question in the chat and we can read it.
Okay.
yeah, it is.
Okay, I'll put it on the chat.
Okay, thank you, Ruping.
No bad. I would like
Yes.
to congratulate you there on your great work, being a former CMC fellow there. I think you've done fantastic work. Who was the project manager for this, basically?
Yes, thank you, Charles. Yeah, yeah, we have a team to manage that. This time we were 4, so there were managers like me. I'm manager now, but there were as well really project managers from operation. So they have a project manager team in operation, of course, to manage these kind of delivery. But in our case, in R&D, we don't have. So that's why it's, I would say. But yeah, that was a big addition to my usual manager duty.
Did you use Gantt charts and things like that?
Use what?
Gantt charts, the project management
Yes.
risk. Did you do any risk analysis on this?
Yes, we do. Absolutely, yes, and it was used. Yes, because there were some issues down the road for sure.
I can imagine the pandemic was a big risk. Yeah,
but it's, yeah, I was impressed by people because they adapt very well to this. Yeah, kudos to them. They did a great job. People work hard, and communication was relatively good, even though we were from home. Because at CMC, it's a big family, so we used to work, research, development, and IT people together. So in the same building, that's that's part of our success. Okay, that's why we compare to other centers in the world. But now everybody was at home, so that's very different.
Are you
context.
going to implement anything to do with ice? You didn't mention much about sea ice and things like that.
Yeah, ocean. Yeah, sea ice was included in oceans. Yes. Yeah, absolutely. We have a sea ice forecast. Yes.
Ruping has typed his question into the chat. He says, "Is the IC3 fully completed and implemented in the operational suite?"
Absolutely, yes. It was everything was implemented on December 1st. Yes, 2021. Yeah.
Jim, you have your hand up.
Hey, thanks. Bonjour, Normand. It's excellent presentation. Great work. Just a very quick question, because coming from my radar background, I'm so excited to see that the radar is now part of. Are you bringing in reflectivity data or just the velocity data?
No, it was. No, it's related to reflectivity, but it's not exactly that. We just take into account the presence of rain, in fact, and modify the vertical structure of the in the model to take into account the fact that there was rain. So it's not, in a sense, we're working now on adding velocity. But it's in that project, it was mostly rain presence, let's say. Yeah, but it was a clear improvement. Yeah, so it's a clear plus for the first, let's say, 6 to 12 hours. There was a gain in predictability, a clear gain in predictability. Yeah.
Excellent.
David Landry has his hand up.
Yes, thanks, Norman, for the presentation. I think it's very impressive work. My question is regarding your epilogue. You mentioned that the complexity of upgrading these intertwined systems is ever increasing, and you're reaching sort of a limit. So from my software background, one of the things that's being done in the industry is try to decouple the different system and have more of a continuous integration or shorter integration periods. So is that something that at all can be considered, or does the dependencies between the system make it absolutely impossible to consider maybe trying and upgrade smaller chunks at a time?
That's a very good question, David. I think we are considering that. One thing that could allow that is to have a continuous parallel run. So then we can add, let's say, modify something on a given month and look for modification in let's say in 1 or 2 months, and then let's say if we're happy with that. So we will need to run everything twice, in fact, all the time, which is a possibility. Of course, you need computer power to do that. But that could allow this kind of continuous integration. Of course, testing, or like unit testing, or these kind of standard testing could help, but because it's complex and it's non-linear problem, sometimes it's not that as easy as just a software modification where you can test if it is breaking something else, when you do a modification. But this thing needs to be evaluated and verified against observation and seeing by a human, So, but I think that's something we have to consider for sure, because it's nowadays it's limiting our way of the frequency of upgrade. Of course, the computer also the upgrade every 30 months. It's putting ourselves in some kind of a calendar that is relatively let's say rigid.
So many things dictate the rhythm of development, other than just what models you want to implement. There's also the computing resources, and
but that's we might move to something more like a continuous integration, but we have work to do to be well prepared for this kind of thing. And it's, I think, integrating more of different parts will help.
There's
Thank you.
one more question in the chat, but I think we should move on to the next speaker. Norman, if you just want to address that question in the chat, that would be good.
Yep, okay.
And stop sharing your screen. Okay, our next speaker is Alexander Huzet. Hopefully I pronounced that correctly, and I apologize if I didn't. This presentation will be on water level prediction, products and services provided by Environment and Climate Change Canada.
Thank you for this opportunity. So basically, yes, before I start, I wanted to acknowledge our colleagues from CMDW and also our intern Logan Yu for developing flooding risk met object. So, and I will proceed then to the outline of the presentation. So after motivation, I'll describe the core systems we use to predict the storm surge. So basically the global deterministic storm surge prediction system. It's newly introduced after the IC3 innovation cycle just described by Norma. So it's a new system. And then the regional ensemble storm prediction system. This is regional system. And then I'll go to the describing the products. So we have gridded products, then marine and coastal lab products, and then coastal flooding risk products. And on the right here, I'm showing you the animation of storm surge simulated during the passage of Dorian hurricane. It's basically just to show you how it distributed in time and in space as well. So how it evolves in time. Basically, you can see when it's red, the high water level due to storm surge increasing and impacts Halifax and other ports. So basically, storm surge and high water level already MSC is issuing warnings for Atlantic Canada. It's in place since 1990, but again, our domain of interest is more than that. And nevertheless, we also have MSCs providing hazard information like wind speed, direction, and wave height. And to fix this limitation of Atlantic Canada, there was a 2019 emergency management strategy for Canada led by Public Safety Canada. And ECC in that was mandated with predicting and alerting coastal flooding initiative. In this initiative, we want to expand flood forecasting capacities for all coastal regions in the country and include Great Lakes and St. Lawrence River regions. For this also brings opportunities to improve our products and services, especially for emergency management. So we improve the service for across the country when we go global, and we also provide early warning about the upcoming coastal flooding events, and we also provide this warning and access to this warning 24/7. And as we go global with ensemble system, also we'll be also able to provide the uncertainty associated with the warning. So now I'm passing to the description of the core systems that we use for storm surge prediction. So in the first column, in the second column, let's say we have GDSPS, the global deterministic storm surge prediction system, and then second one is regional ensemble storm surge prediction system. Both they have spatial resolution of 1/12 degree. The global one is based on NEMO concepts, and it's barotropic, and Dalcos is all barotropic. So the ensemble system is based on Dalcos model. Both of them model tides to provide the total water level, and they do two forecasts per day at 00 zoo and 12 zoo, except that the ensemble system, it issues a bit longer forecast for 16 days. These are just limited by the atmospheric forcing we get for deterministic from global deterministic prediction system and from JEBS for the ensemble. And we also anticipate in the next upcoming innovation cycles to improve the global deterministic system by including the interaction of storm surge with the CIs and include the light bar clinic mode. And the ensemble system, of course, we want to go to the global ensemble storm prediction system so we can serve all the coastal regions in the country. Just one note about the GDSPS storm surge. The GDSPS is based on NEMA and it does not output storm surge directly. So we have to do a bit more work in the post-processing and derive the storm surge, basically to analyze, to apply the harmonic analysis with T-tide and produce the tides and then remove them from the total water level to get the storm surge. As you see, that the domain is a bit limited here, just we don't want to waste resources. And then we get the time series for each point. We get time series for storm surge and total water level. Here I'm showing it in red, the total water level, and in green in storm surge. So here I'm passing to the products. So we have two categories of products for GDSPS and RSPS as well. So we have raw data. It's a kind of it's still a process, but we call it raw. And then the post-process data, we add even more value to the data. So we have storm tide. It's basically total water level with respect to mean water level and storm surge. The outputs are hourly, and we already have it in netcdf format on Datamart website. It will go to GeoMet. GeoMet is a web service that provides the mapping interface, so you can query it and embed maps in your applications. It's coming in late 2022 for the storm surge and total water level. To even make it more useful to the users, we also provide a storm tide total water level reference to the highest astronomical tide and to the lowest astronomical tides. Basically, if you have water level approaching highest astronomical tide, then you have to expect flooding and you have to be worried. And for the lowest astronomical tide, it's also flagged for navigation. We also have some internal websites like Marine and Coastal Lab page and Nino, and the post-process project will go there also in late 2022, as well as on GeoMet and Datamart. These are RESPS products. It's mostly similar, except that we have more statistical outputs for the RESPS products. We have median, interquartile range, means, and standard deviation percentiles. And we also plan to ship it on GeoMet 2022. But the data, raw data, is already available on Datamart in netcdf format. And the outputs is also hourly. So now I'm going to talk about the marine and coastal lab products. So basically, this is on the left. I'm showing you the interface that meteorologists within the storm prediction centers see on their desk in their web browsers, and we also can access it in Environment Canada. Basically, it's showing you the important points color coded. So when it's green, it's okay, there is no flooding, but there are different stages of flood. So stage 1 is a minor flood, and if it's orange or red, there is a flooding. But the meteorologist is not supposed to open it and watch it every day and check whether there is a flood or not. There is a system, a post-processing system in GDSPS that actually analyzes the data and checks if those certain thresholds are exceeded. Then it's generates XML files and also text bulletin, and notifies by email the mailing list. So when the meteorologist receives an email about the flooding event, he can actually go and check which points are blue or yellow or red, then click on that point. When he clicks on it, he's presented with the time series like this for different points. It depends on which point he clicks. Here's an example for Kappa Mall. And it's showing you in orange, the model total water level, and green is the observation data. And this pink line, the horizontal pink line, is the highest astronomical tide. And you can see that the total water level actually exceeds the highest astronomical tide. So it might be a sign that you might expect some flooding in the region. And in the blue line here in below is actually analyzed the model, the storm surge. We also have on this graph the tide prediction from DFO, from fishers and oceans. And we derive the pink line is kind of like observed storm surge, basically by removing DFO tides from the observations. We have a similar point of outputs for ensemble system. So here it's actually was around for a longer time. So we have an example from Hurricane Teddy, happened in 2020 near Halifax. So we can see from the forecast that in red shaded area, we have storm surge, and the blue, it's a total water level. And we can see when we look at the total water level that we go into stage 1 flooding. So we have to, we have to issue a warning and warn people that might be minor flooding in Halifax at that period. So basically now I'm passing to the last type of products. This is coastal flooding risk products. This is the newest product we got from CMDW, and many people were involved. So basically how it works. So we have the outputs of regional storm surge prediction system, and we have percentiles of the maximum total water level for the next 24 hours. And we get the thresholds indicating different severity of flooding. We get from provinces and territories, from governments. And then we combine this information to produce a map like here, the third one. And this is kind of like a combination of severity of the flood and the probability of the flood. So if most of the members exceed the highest threshold, then we mark the grid cell with red, and that means that there is a high probability of severe flooding. Well, this map, of course, goes through a forecaster, and if there is nothing, if forecaster seems it's correct, he checks, and also based on his experience, then it goes to product generators and then it's dissemination. So just in conclusion, I hope I convinced you that ACC provides useful deterministic and ensemble water level products for short and longer lead times until up to 16 days in ensemble. And we also are very lucky that we have this predicting and alerting coastal flooding initiative that is catalyst to improve the product, but as well it can be like feedback for us to improve the model and also constrain the model to perform better. And these products also supposed to be extended to serve from the high resolution ocean and Great Lakes model, COPS and WCPS that Norman already mentioned. So now here are the links to the scientific articles and also documentation and data available from DataMart. So now I'll take questions if we have time.
Great, thank you. We have time for a couple of questions. You can either open your mic and ask your question here or type them into the chat, whichever you prefer. No questions? Okay. Well, we'll move on to the next speaker then. The next speaker is Judy Kwan, and Judy will be talking about visualizing Canada's daily climate records in 2021, placing high impact weather within a historical climatological context. Go ahead, Judy, share your screen.
Hopefully everyone can see that.
Yeah, just put it into presentation mode and you should be good.
There we go.
There, perfect.
Hi, everyone. Our poster, we are in this session, we're doing an introduction to the poster that we have on display in the poster session. The title of our poster is called Visualizing Canada's Daily Climate Records in 2021. And we're placing high impact weather within a historical climatological context. So I'm very happy to be here today. My name is Judy Kwan. I am the section head of the new Applied Climatology West. First, I'd like to acknowledge my co-authors for the poster. I have Rachel Chen, who is our physical scientist, as well as our GIS scientist, working out of my unit, as well as Nabila Doctor, who is our data scientist, as well as our student out of Simon Fraser University, and Ruping Mo, who is out of Applied Science, our national lab in the West. There's our poster on the left-hand side. I won't have time to go over all of it, as I only have 5 minutes to kind of give you a little bit of a snap into the poster. I know you can't read it all, but what I wanted to go over in terms of introduction, if you're interested in our poster, you can download it and take a look and contact us. The key thing with our poster, it's a little different than the other talks, is it provides new data visualization utilized and developed during the high impact weather and climate events in 2021. We look through the data through the lens of daily climate records. So not from a weather perspective, it's a weather climate perspective, but specifically looking at daily climate records. The examples we highlight on our poster looks at the heat waves of summer 2021, as well as the extreme precipitation events of November 2021. The background covers just a snapshot on the top of what do we mean when we say daily climate records. The key data using is one that's published by MSC called the Long-Term Climate Extremes for Canada. Normand's presentation had a lot of links to the MSC's open data documentation, and in the bottom left-hand corner of the poster, I do also have links to this data set, as well as the links on how you can access that data. One key thing that's different with our data visualization and our data analytics is we actually utilize MSC's GeoMet API platform to access and integrate hourly surface weather observations together with our daily climate records. So the last point I'll make that's a bit different perhaps in our poster is the software and technology stack that we're using is our studio, our server, Shiny server, and the shinyapps.io in the cloud, in case people are already using R, but maybe aren't aware of the shinyapps.io in the cloud. We do a citation to the R libraries that we used for data manipulation, exploration, and visualization. So it's not all the libraries, but the ones we thought were kind of nifty, they're kind of cool, and we found them really useful. And so we also, again, have them cited in our reference in case people want to implement them for use. So just a couple of poster highlights and examples I'll go over. We use R for interactive web mapping. We find that using developing custom web maps is super useful, not only through an event, but for our users throughout the year. So we develop color-coded map dashboards. So the first one I'll take a look at here that you see in the middle here is very easy, very user intuitive. If your marker is red, very pleasing to the eye, it grabs your attention. So this one's a snapshot of June 27th, 2021. This is how this dashboard looked. We have 45 potential record highs. That's happening at 19 Zulu. In the legend, it'll give you a count, but right away you can see exactly where those red markers are. In the purple is the ones that are approaching the record high. If we wait a few hours and we check back on the dashboard, immediately we see we have 91 potential record highs. And so very easy to understand, really useful for our users. Another way we use interactive web mapping in terms of a web map and color-coded map is if you click on any one of the markers, it pulls up a 7-day window. On the 7-day window, this is an example for Lytton for June 28th. Across the top is showing your historical record highs. Across the bottom is showing your historical record lows. In the middle is today. And if today was June 28th, 2021, we pull in two columns. One is pulling the historical high and low, as well as then we pull the observation. So a real-time observation coming out of GeoMet, which is our hourly swab, and we run that for comparison. And it controls the marker colors. Very quickly, we also really love using R for dynamic and reactive graphing. So that's for interactive daily time series. And so we I think for this audience, it might not be that new to do a daily time series, maybe a monthly time series. We do a variety of different chartings, including daily extremes and monthly extremes. So here we have an example of daily precipitation out of our Abbotsford site for November the 14th. We can see that the record high, the daily total for the day is over 100 millimeters. It's interactive where our users can click on the dots, okay, that are showing up on your graph, and it responds and tells you the value. Over on the bottom here, we have widgets that we add, which can quickly control and have a reactive graph. So you can see when was the last time this occurred, how often does this occur? So the widgets add easy filtering of the time series for any analysis we might need to do, as well as controls dynamic graphing. Something that we're fairly newly testing is monthly time series. So summing the month and visualizing that in terms of a top 5 rank. And so here we have, again, Abbotsford. If we look for the month of November, we can see by the end of the month, we have over 540 millimeters. It's our first wettest month of November for that station. And we could see when we graph it in our top 5 that it's significantly higher than the previous Novembers. There's a lot more to see, but I think that's about all the time that I have. We also use R for animation in our post event. And up here, what I'm looking at is new record highs through the heat wave. And so we can see every single day where those highs happen, as well as we time step that through every single day. And even just as a note, for June the 29th, we have more than 5 sites within BC that is greater than 45 degrees. So we can see the magnitude of those records, the number of records broken, and just seeing it spatially as well as temporally makes it much easier to convey the impact of such a severe event. If people have questions, they can ask us now. I also want to highlight, yeah.
I'll just point out that this, I think the poster discussion session for this is tomorrow. And just to remind everybody, that's moved to GatherTown. So go into GatherTown and find Judy's poster and we can ask questions there.
Thank you.
Thank you. And with that, we're pretty much right on time. So we'll move on to our next presentation by Xiaolan Wang. And the title of this presentation is On the Development of Canada's Homogenized Precipitation Monthly Dataset. Xiaolan, can you share your slides? And
I'm trying. Can you hear me?
Yeah, we can hear you.
Okay, good. Oops.
Judy, you might have to stop sharing and so that.
Do you see my screen now? Because I can't see the.
No, we still see Judy's screen. Judy, are you still there? Can you stop sharing? Can I do that? There we go. Okay, go, Xiaolan.
I can see only my screen, my presentation, nothing else. So, okay.
You have to hit the share screen button at the bottom of the screen.
I did.
And then
wait a minute. I think I need to do it again. Can you see my screen now?
I think it's coming up. There we go. So just change to presentation mode. Ready to go. Perfect. Go ahead.
Okay. Thank you. Good morning, everyone. Today I'm going to talk about our work on developing a homogenized precipitation monthly data set for Canada. As an introduction, I will talk about why this work is needed. Then I will talk about those data sets used and the selection of the core long-term stations. Then I will talk about the data homogenization procedures and show you the results. And then at the end, I would show you the effect of data inhomogeneity on trend estimate. As many of you know, that Canada's precipitation trend assessment has been based on the 463 ASTD precipitation stations. All of them are manual stations. The number of stations with observed data in this network has been decreasing rapidly since early 1990s. So most of the stations were either automated or closed. And the challenges are the use of manual stations alone can no longer provide robust estimate of trends and the climatological mean precipitation, as is shown here, the regional mean precipitation for the north. This is from the 71 stations here shown here, and this is from the 463 stations. And further, automated gauge data are often not very different from manual gauge data. So joint data series are very likely inhomogeneous, and the different stations data record cover different periods and include missing data, which notably bias trend estimate. And this is the work by one of our postdocs, which shows that trend underestimation severity increases as the number of stations or data decreases, and which is much smaller effect in the south because of a higher density. And this also showed that even the network of 463 stations is not sufficient to represent regional precipitation trend in the north. And that look at the truth is in black, and the blue is from the 463 stations. Now about the source data, the first one we use is the adjusted daily rainfall and snowfall data sets. This data set includes over 3,000 stations as shown here, most of which are in the south and of short records. Different versions of this data set were used to produce the unspin gradient adjusted precipitation data set and the Kappa precipitation reanalysis. The second data set we use is the archived daily total precipitation from the automatic gauges shown here. And we also use unspin gradient adjusted monthly precipitation data set, as well as the 20th century reanalysis version 3 ensemble bin series of precipitation, of monthly precipitation. The latter was used only as reference to detect change point, not used to make adjustment to station data. In selection of the core long-term precipitation stations, we consider the need for future proof because it's difficult and very time-consuming to do precipitation data homogenization. So it's very important to ensure that the chosen stations will have good chance to be operated and well maintained into the distant future to produce complete good quality data for decades to come to ensure longevity and temporal consistency of observations. And to this end, we started from the currently active automatic gauge data that are producing good precipitation data and from the designated reference climate stations. We chose, excuse me, we chose all stations that have collocated or nearby stations of precipitation data to form a long-term precipitation time series. When choosing the most suitable nearby stations to join, we consider the correlation between the stations as well as the names and completeness of the data record. For data sparse areas, we also allow stations of shorter or poorer data record to be retained to infill critical spatial data gaps. And we also try our best to have a higher staging density for areas of complex topography or of spatial, low spatial correlation. And as a result, we came up with these 426 core stations. As you can see, there are still data gaps in the north, and 40 of these stations are not MSC stations. They are shown in pink. And also many of these stations were closed or no longer reporting precipitation including many RCS stations, because the selection of the station was done about 3 years ago. We also used the Arnold Spin estimate of monthly precipitation for the station to infer the temporal data gap in the data series. And as shown in blue here, the Arnold Spin estimates are very good for some stations or periods, but are systematically biased for data sparse areas or periods. Nevertheless, the gap inferring greatly increases the robustness of change point detection and data homogenization result because of the significant increase of sample size. For homogeneity testing, we applied the test in our RH test package, which is a data homogenization package, to the log transform gap inferred monthly precipitation series. And we conducted tests with and without using a reference. And we accounted for both type 0 and type 1 change points. We used 6 references, including 4 best significantly correlated neighbor stations. And we investigated metadata to infer all potential type 0 change points. And we also use periods of missing data as a piece of metadata information to find potential type 0 change points. And we developed automated procedures that first screen in all potential change points and then screen out insignificant ones one by one. At the end, we manually investigated station by station the result obtained from above and to obtain the final list of change point, one list for each station. And all the change points in the final list must be significant at 1% level when tested with and without reference. So it's a very strict test. And this shows the examples of inhomogeneity. As you can see here, some of the shifts, we know the cost, like these ones are from joining of stations, but some of them are not. They are called type 1 changes. They are statistically detected and to be significant change point. And these are just a few more examples that I want to draw your attention to the sudden drops at the end of the series and also a lot of missing at the end of the series, which is a common problem with automated gauge data. Okay, so in total, we detected 744 change points, and at 1% significance level, 130 out of the 426 data series were found to be homogeneous, 296 are not. The percentage of stations with at least 1 change point is higher in the early period and in the recent decades, and it's lowest since from the mid-60s to about 1990, and it's highest in 2017, reaching almost 13% of the station. And this is also true for the type 0 change point. But for the type 1 change point, those that we don't know the cost, the percentage decreases over time, thanks to the, shown here, thanks to the improvement in metadata collection and the more missing data in the recent decade as well. For the adjustments to diminish data inhomogeneities, first, we identified the best significantly correlated nearby stations of a homogeneous segment that includes the highest number of base series change point to use as reference to adjust the base series for the change point in the base reference overlapping period. And this procedure adjusted 601 out of the 744 change point. Note that 22 out of the 296 inhomogeneous stations don't have a nearby best homogeneous segment within 300 kilometer radius. Then we made adjustment without using a reference for the remaining 43 change point that can be adjusted using the procedure one above. And we adjust the series to the longest observed segment. And the adjustment was done to the log transform base series, which was then converted back to the actual precipitation values to obtain the adjusted precipitation data series. And we made only mean adjustment, not using quantile matching adjustment for this version. However, the mean adjustment to a log transform series are multiplier adjustment to the precipitation data series. So the variance is also adjusted to some degree. As you can see here, the first panel is the raw data. The second one is the mean adjusted homogenized data set. You can see that the huge variance change here is also adjusted to a large degree, and also in this segment. Okay, this shows the effect of data inhomogeneity on the trend estimate because of the non-Gaussianity of the precipitation series. We use Mann-Kendall estimator and we apply it to the deseasonalized monthly series. As you can see that the homogenized, the left panel is the raw data, the right panel homogenized data. The homogenized data shows slightly better spatial consistency of trend. And for a few stations which are of spatially inconsistent trend, they are actually homogeneous stations. So the inconsistency of trend is not a result of data homogenization. And this shows the trend in the homogenized monthly precipitation series for the period since 1948, and this one for whatever period the data has record. So we see that most significant trends are increasing in this southeastern region, and as well as in the Arctic and the West Coast area. That's it. Thank you very much.
Great. Thanks, Shalane.
Should I unshare it now?
Do we have questions? I have a question. As you know, we recently completed the wind adjustment for 397 of our RCS stations. Are you planning on incorporating that to see if that has a impact on inhomogeneity?
Are you talking about the Giono and Pluvio
Right,
station?
the auto station.
Yeah, yes, it will be, but not in this version. It wasn't ready when we were doing this.
Right.
Yeah. So, but we have the homogeneity test and adjustment. So even for the segments of the Giono and Pluvio data, it's adjusted. It's homogenized statistically.
There's a question in the chat, but perhaps it could be answered in the chat.
Don't know. I have to. How do I get out of here? I can't see anything but the presentation.
Just hit escape.
Escape.
And then you can stop sharing your screen.
Yeah, I hit escape. Nothing happened. I stopped sharing. I think stop sharing.
There we go.
Yeah.
Good.
Here
Perfect.
we go.
Yeah.
Okay.
Yeah. As
Ron.
Ron said, there's a question in the chat, but we're going to move on to the next presentation, and maybe you can just address the question in the chat, Shalane.
Yeah.
Okay. Thanks. Our next speaker is Jim Young. Jim is going to be talking about a preliminary look at machine learning model improvement of quality control of MSC surface observation data. So good, we can see your screen, Jim. Go ahead.
Perfect. Good day, everyone, and I hope everyone's doing well. My name is Jim Young, and just gonna flip over to my other screen here. Just a second. There we go. Oops. Oh, that's not good. There we go. And I have my co-authors and co-presenters here, Tanesh and Adam. Maybe I'll ask them to turn on their cameras as well, and they'll be presenting a few slides here as well. In the last 5 years, I've been working as the manager of the data management operations section. So we're gonna get started. We're gonna have a couple of slides here. We're gonna do a very, very high overview of the MSc monitoring data and touch a little bit and spend a bit of time on the data quality control system. We'll touch upon the bulk of our time will be spent on the anomaly detection using machine learning model, and we'll present some early results and some of our limitations, and we'll do a quick review of our path forward going forward. So the monitoring data is really a collection of a number of different networks. We bring in networks from all over the country, as well as some international data. And we bring in different types of data all together. And so what we do is we actually have a number of inputs to help with the forecasts, with the historical data and alerts. We provide input into climate change and into different natural hazards. The boots on the ground, so what's called the boots on the ground, include collecting data from a variety of different surface environments, such as ground stations, hydrometric stations, weather radars, marine buoys, weather balloons, and of course our satellite ground receiving stations. And we have over 10 million observations that we collect, and we standardize into a common format, and over about 17 million automated quality assessment tests are performed daily as part of our overall quality control landscape. Turn over the time to Tanesh.
Thanks, Jim. So in the MSc, we have a system called the data management system that receives and processes data in real time, both from our own networks, the MSc networks that Jim mentioned, as well as our external networks that we ingest data from, such as from provinces and territories. So the data management system receives and processes that data. It makes the data available to our end users in real time. And part of that process is also quality assessing the data and attributing the data with quality flags. We have different flavors of quality assessment that we perform. There are 4 of them. We have the native quality assessment or native QA flags, which are incoming quality attribution with the data from the data providers themselves. So this can include whether data is suspect or is suppressed, maybe indicating that the data is not to be used by the end users or in products, or it could be that indicating that the sensor is not active, for example. Building on that native quality assessment, in the data management system, we perform various different real-time quality assessment. This includes presence check, checking to see if the value is actually there when it's supposed to be. Integrity is the value of the format expected. Is it an integer? Is it a string value of sorts? Or looking at the integrity of the data. Range, we do a pretty sophisticated list of range checks to make sure that the data conforms to various different ranges for acceptance and doubtful and suspect. We also compare the data against other variables if there's correlations between multi elements, as well as temporal checks. We look for spikes and dips in the data as well. We are working on near real-time assessment as well for enhanced temporal and spatial checks. And finally, we do manual quality correction. And this is really the focus of the presentation here, is how do we optimize and streamline our manual quality correction of the data. So these are the systems and processes that we have in place to ensure that we fulfill our mission, which is really to make known and high quality data available to end users. Next slide, please. So in our mission to sustain and improve the climate data quality of the data that's managed in our National Climate Archive, we employ various different manual review and correction of the data to identify and investigate outliers and correct them to maintain the quality of our climate data. And we use various different guidance to help us navigate that. We focus on high visibility stations and parameters. We look at stations that had the known issues or product bound data. If the data is going to be displayed on a public designation portal, or it's going to be sent to WMO, for example, in a normals format, we focus on those. We also focus on anomalies reported by end users. Somebody sees the data on climate data online or other external endpoints, and identifies a possible issue. We also investigate and correct those. But even with these guidelines in place, it's still a bit like finding a needle in a haystack, looking for these outliers, just dealing with the large volume of data that we're dealing with, both real time and on hourly and sub-hourly frequency. So we need an automated approach to identifying these outliers and correcting for them. And that's really the focus of our investigation here. Next slide, please. So we looked at anomaly detection and automated anomaly detection as a way to reduce that manual effort that goes into quality correction. It's not a new concept. It's something that has been used very heavily in other very data-heavy disciplines, like such as in the financial, medical, and other operational streams. And so we applied an AI approach to anomaly detection to find outliers that doesn't conform with historical or current norms, to help us reduce that search phase of outliers, so that the QC technicians can focus on investigating those few anomalies and correcting for them, rather than looking for those anomalies. I'll turn over to Adam now to explain the AI model that was used for this approach, as well as the model performance.
All right, yeah, so thank you, Tanesh. So now we'll be getting a bit into the technical side of the model that we were using. And so here we have like 3 graphics which sort of capture the inner workings of the model. And so on the left, we have a data flow diagram that shows the end-to-end process that the data goes through as we use this algorithm. And the key thing to sort of take away is that we're on the one hand selecting some training data. So we select some station list, and some element like maybe temperature, precipitation. And then on the other hand, we select some testing data. So again, we select some station and element. And then what we do is we make predictions on which observations are going to be overturned in the testing data based on the historical observations that are present in the training data. And then so if you look at the diagram in the middle, that's sort of a graphical representation of a random forest algorithm, which is the specific algorithm that we're using to make those predictions. And the key thing about the algorithm is that it just makes a sort of binary prediction about whether or not the observation is going to be overturned. So in all of our testing data, it just makes a prediction, yes, this observation is going to be overturned, or no, it's not going to be overturned. And then if we look at the third graphic on the right, we have our top predictor variables. So the idea here is, machine learning algorithms can be a bit of a black box. And what this does is gives us a look at what is actually going on inside the algorithm. And so if we look at the top predictor variables, we see that it's a lot of the snow depth Q. This is specifically for an instance of snow depth error prediction. And we can see that a lot of the snow depth QA values are the top predictor variables. But in addition to that, other stuff like the hour of the day and the panel temperature are being incorporated. So we can see that stuff outside of the traditional QA process are being incorporated into the predictions made by this algorithm. Next slide. Thank you. And so now here we have some results, some metrics. So as you run this sort of algorithm, you can, figure out certain metrics and identify where the model is performing better. And so those 2 key metrics are precision and recall. And so that essentially just tells you how accurate the model is at finding anomalies. And what we found was that we had the best performance for 3 elements in particular: for snow depth, wind speed, and precipitation. And so each of these graphics correspond to that. And in addition, we found that we could expand it to many different stations. So we were looking at high impact CLIMAT stations, but we found that even stations which didn't have as many historical anomalies we could still make predictions on that data. And then if we move to the next slide. Thank you. So here we see some limitations. So just because of the way that machine learning algorithms work, you're really limited by the historic data that you can feed into the model. And so the model's predictive capability is essentially as good as the corrected data that you're feeding into it. And so that's sort of just one limitation, that you're just limited by the quality of the corrected data. Then a second limitation that you come up against in relation to that is that it's very hard to make predictions for anomalies for data that don't have a lot of historic anomalies. So something like station pressure and temperature have very few historical anomalies. So there's just really not a lot of material there to make predictions for using this approach, which is why we sort of focused on precipitation, snow depth, and wind speed, because that was where we found the greatest amount of historic errors to use in our predictions. So I think I'll pass it back to Jim now, if I'm right.
Yeah, great. Thanks, Adam.
Yeah.
So, as we look forward, it's always a good idea to know where we came from. We started out with an idea way back in 2018, which germinated into a small contract to help provide sort of the initial machine learning model. And so far in the time that we've been doing this, we've been increasing sort of the model's capability with new data and additional stations and elements. And really, I want to point out here as we go forward in time, the explainability of the model is critically important for both the acceptance and the trust in the model results as we go forward towards at some point in some type of an operational mode. So the future looks bright, and with that, we'll end the presentation here, and we'll open the time for we have some time for questions.
Great, thanks, gentlemen. Yeah, we have a couple of minutes for questions. I see Tanesh has already been addressing some questions in the chat, so great, thank you. Does anybody? I see David has his hand up. Go ahead.
Hi, thanks for the presentation. Happy to see AI being used in weather, one of my pet peeves. Favorite subjects, I mean. Have you mentioned one of your limitations is the number of historical anomalies that you have recorded. Have you considered using unsupervised algorithms to maybe circumvent this limitation?
I'll turn it over to the experts on my team here.
Yeah, so my answer to that would be we didn't really consider that yet. And I think part of why we didn't consider that was because the way that we were sort of approaching it is that we have QC techs who are working to correct the historic data, right? So they either do overturn something or don't overturn something. And one problem that you can run into is that it's very hard to validate whether or not a prediction is actually correct in any way other than using the historic corrections that were made or not made to that data. So our approach is essentially take all the historic corrections that were made, split that into either yes, a correction was made, or no, a correction wasn't made, and then just use that as the sort of target variable that we were going after. That was like the approach that we took. But yeah.
And to that point, we have been kind of forward-looking into incorporating NWP outputs as another kind of independent validator. So we make a prediction, and we would use the model and any other sources to say, is that really an outlier, and is there a correction needed? So that's something that we are looking forward to incorporating down the road.
Thank you.
One more quick question, Naman.
Yes, so yeah, very interesting. Do you plan to retrain the algorithm every month, or what is the plan for the? I would say that was a test I saw with 2 years of data and test on 1 year. But let's say in operational context, do you? What do you envision as a framework?
Yeah,
let's say?
Yeah, that's a good question, Noman. And really, the operational context is going to be pretty far away. A lot of this work has really been done on the side of our desk. Actually, it has been all done on the side of our desk, and was really given, what I call the Google time. 10% of your time, 15% of your time from your normal day job was dedicated to this. So I don't know, Tanesh, I don't know if you have any comments on your thoughts on going forward.
Yeah, no, that's a very good question. So we are planning on putting this into a semi-operational mode where it's continuously training itself. So even the predictions that the model makes and the quality technicians correct, they'll be fed back into the model. So we want to set that kind of a data process in place so that the model continues to be trained on ongoing operational corrections that are being made to the data on a daily basis. So over time, we see the performance improving by doing that.
Yeah, we can talk more on that, but that's interesting.
Good.
Yeah.
Great. There's I think another question or two in the chat that you guys can address, but we should be moving on to our last presenter of this session, which will be Nanar Jacobs, and I apologize if I didn't pronounce your name correctly. The title is RADARSAT-2 and Sentinel-1 for assessing ground displacements at the Hay River Airport, Northwest Territories, Canada. Nanar, can you share your screen? Actually, I don't see him in the participants list. Does anybody know if this paper's been withdrawn? Okay. All right. Well, I guess that means we can open up the chat for any to any of our other presenters. Ron, is there any questions in the chat that we haven't addressed yet?
I think there is one from David. And Ying as well.
Okay, so there's one from Ian Russell to Ian. Did you want to just open your mic and ask that question? I'm not sure who it's addressed to.
Yeah, it was for Finesh or Jim. It just occurred to me that NWP data assimilation is checking the difference between candidate observations and a background field, and I wondered if that process could be used to help inform the observations quality control.
Yeah, I'll start and maybe Tanesh can add on to it, but yeah, definitely that's definitely been something in our minds already. We've been looking at adding the NWP outputs and really, taking a look at that and even actually including that into our overall C framework.
Yep, exactly correct. So yeah, we do plan to incorporate that data set as well. We're basing our model training so far on historical climate data, but moving forward, we do want to incorporate the simulation outputs and flags as well into the AI model.
Thanks, Tanesh.
Charles, you had your hand. Go ahead.
Yeah, this is Charles Anson. I used to do data quality on radiosondes, and one of the problems was the temperature things that, and we had to change the actual radiosondes to improve this. And this did come from the background fields. So I'm wondering do you have any Canadian radiosones that are still suspect at the moment? And maybe I could address that to Norman also as to who's doing, are you still doing sort of quality control for things like radiosones at what used to be CMC?
I was going to say Norman is the person to talk to there.
Yeah, Charles, since you left, huh? big hole to fill. So of course now we're moving to automated let's say, monitoring, but that's a good question. Every cycle, every 6 hours in our data simulations cycle, as mentioned by Yin, we do comparison with the background check, what we call background check, which is a short-term forecast information on these, and we have information on every, in fact, observation that we assimilate. So that's the idea. Here we're talking more about surface data, which is by itself a whole universe, because there's a lot of local effect, and we need high resolution to be able to do that carefully. And now we have an assimilation system at 2.5 kilometer, which probably will be more suitable to do this kind of thing.
This was with radio songs. CCMEP, of course, still is doing. They probably still produce their lists.
Yeah, we exchange that every few months. Yes, we have well, of course, yeah, we do to identify a station that are not working very well, but yeah, so for upper air it's quite, I would say, well established. For surface, as mentioned by Jim, we want to link together our two groups and doing improve quality control. But that's so, of course, we have a lot of information that could be fed to this kind of AI system, and that's very interesting, I think. And the fact that it's automated, that's
very good.
That's hope for be able to do it. Because now we assimilate millions of data per day, so we cannot have a Charles looking at manually everything.
Yeah, that's really the whole driver here. Is that with the amount of data that we're bringing in, there's no way we can do this manually. No, it's impossible.
Yeah, even for AI, could be a challenge.
Yes, but in a sense, I was doing it automated, but I had to produce a list. But that was just. I agree. We've gone. That was 17 years ago.
Yeah, with some of our surface stations now, they're moving to collecting at minutely data. So so imagine that, right? It's just
it just boggles the mind.
Boggles the mind. You never thought that was possible before, but now it's actually happening.
Yeah, and even we're looking at other types of data, like IFT data. So this could be, that's probably will need a big cleanup.
Yeah, and if you can imagine in the future, even the Internet of Things, right? All those other sources of data that's coming in with all sorts of different quality types, right? So I mean, I say that as a data person, the future is bright. I'm very excited about that, but it's a big problem too.
Yeah, it's bright, but at the same time it's dirty. So. But absolutely, we need data for sure. That's yeah.
I think one of the biggest problems is biases of the actual data. Whether this is basically what all this is bias. Is that and change of instrument can be as bad as anything else.
Mm-hmm.
Yeah, well, Internet of Things, there are many things to consider in that. Representativeness, and it's going to be quality, as mentioned by Jim, but bias, of course.
Location bias is going to be a problem, right? These are all you can all think of it as problems or opportunities, right?
Yeah.
Good. Any questions for other speakers in the session? No, if not, we can close the session and remind everybody that the plenary talk begins this morning at 10 Central, so 12:30 Eastern. And today's plenary will be Deborah Wunsch